in problem 28, we're going to find the domain, well, the range, actually, of some complex functions with a given domain. So for part A, the domain is the closed disk. So let me be clear. The domain is here, and it's the closed disk of radius 2, centered at the origin. It's closed because we have a weak inequality. And if we think back to regions in the plane, shapes or regions rather that are defined with a weak inequality, so the or equal to part, are usually closed. But we actually looked at this when we were talking about those types of regions. Okay, so we want to find the range. Now, the range is not the same as the codomain. So in this problem, the codomain is implicitly all of the complex numbers. This is very much going to be not equal to the range. So what this is asking is, what are the actual outputs? So the codomain is the allowable outputs, and the range is the actual outputs. So let me just notice something here. If we were to write our z as a function of x and y, this is just the imaginary part, so it's y. So we want to know what values can y take on. That's the range. Now our inputs are the closed disk of radius 2. So let's just graph that real quick. It's always helpful to stare at a picture if you can. So we'll go 1, 2, 1, 2, and here it is. Now I've never been able to draw a circle, so forgive me. And then our closed disk is here. We have those points. Now our function, what it's going to do is it outputs the y value. It outputs the imaginary part. And the imaginary part is sort of our height, if you like. So this is asking, what heights do we achieve? And if we look, we achieve all heights between -2 and 2 inclusive. Inclusive because there was a weak inequality here. So what's our range? I would say the range of our function is the collection of complex numbers such that there is no real part. So 0 plus, we could write it like this, 0 plus iy, and our y is between -2 and 2. Or we could say it's the collection of all z's and c such that the real part of z is oh shoot, I messed this up slightly. Oh, okay, so I made a slight mistake here, but we make mistakes. Let me go back real quick. We don't actually output I times y. We don't output I times the imaginary part. We just output the imaginary part. So let's go back real quick. This is the outputs will be purely real numbers. So it's actually the set of all y's plus no imaginary part, where y is between -2 and 2. Or we could write that as the collection of all z's and c, such that the imaginary part of z is 0, and the real part of z is between 2 and -2. Those are our actual outputs. So for example, to kind of visualize what's happening, our point here, 1i, has imaginary part 1. So our function is going to take that point and it's going to spit out the number 1, which in the complex numbers is here. Okay. So if we liked, our function is sort of look directly over on the line y equals -x. Similarly, this point, which is at 3/2 I, is going to go to 3/2, go to over here. The function is sort of look directly over there. Okay, so here's an example of computing a range. Let's do one more example because I even confused myself, so it's a little bit confusing. So let's do part B of this. So part B asks us to consider the function 1 plus I times modulus z, and we want it to be defined on the unit square. So the unit square is the square of side lengths 1 in the first quadrant that sort of sits as close to the origin as possible. So our real part is going to be between 0 and 1, and our imaginary part is going to be between 0 and 1. Let's just graph that, because that's, I think, our first time talking about the unit square. So if we go over to 1 and 1, these are all numbers that have real part between 0 and 1 and imaginary part between 0 and 1. So again, here's our real axis and our imaginary axis. Okay, so so that's the square, and it's inclusive everywhere. This is to remind ourselves some of the language. This is a closed, connected, bounded region. It's not relevant for the problem, but satisfies all of those properties. Now our function f of z is going to be 1 plus I times modulus z. So what is this? Well, if we take modulus z, which is just a real number, and we multiply that real number with the complex number 1 plus I, which we could think about as a vector, then what we're doing is we're sort of looking at all scalar multiples of that vector, where the modulus of z, so not all scalar multiples, but the scalar multiples where the modulus of z is in this range. So I think to better understand the range, what we should do is we should first better understand what outputs the modulus z can be. And let's notice here, in the unit square, let's call this, let's call the region R. Let's call it R. In R, the modulus of z takes on the value 0 at the origin and is largest at the point 1 plus I. Right? We're furthest away from the origin at this point here, 1 plus I. And the modulus of 1 plus I, let's see what's the best way of saying this. And, I guess, modulus 1 plus I is root 2. So this is telling us that the values that the modulus obtains in our region is 0 to root 2. And it obtains actually all of those values because the modulus is just the length function, and the length is a continuous function. So if you obtain, well, there's some topology here, but if you have a continuous function on a connected set, the intermediate value theorem holds. Namely, you attain all values between the smaller value and the larger value, the smallest value and the largest value. Okay, nevertheless, these are the values the modulus obtains. So what does our range look like? Our range, oops, I've been using blue. The range of our function is going to be the set of all 1 plus i's times r, where r has value between 0 and root 2. And if we were to graph that, that's not part of the problem, but if we were to graph it, what would it look like? So here we have 1 plus I. When we multiply 1 plus I times 0, we're going to get the point down here. And as our multiples get bigger and bigger, we're going to be on a line through 1 plus I. And our line 1 plus I, our ray rather, through 1 plus I, and the ray sort of ends at some point, so we get a segment actually, and it ends when r is the maximum value it can be. And what is that value? It's root 2, so then what's the modulus of 1 plus I times root 2? Well, you'll find it's 2. Okay, so that means that it starts off at 0 and it goes out along the vector 1 plus I until we get to a maximum size of 2. And so if we were to graph the range of our function on that set, we get that picture. We get that picture there.